Thank you for the invitation. It's nice to come here because Riverside has a pretty awesome particle physics group. You guys have a strong group both in theory and experiment. Some of these folks I've been collaborating with since I was on D0 as a grad student quite a few years ago. And it's nice to see faces here in experiment and in theory working together. And not only is it a strong group, people doing good science and thinking about hard things, but it's also it's a friendly group. And I know that because at least a couple of these faces, Flip and Hybo, used to be Irvine postdocs, so I got to know them. And how can I convince you that they're not just smart, they're also nice people? Let me give you an example. They like to help out. So for example, one day when my young son needed to do his homework, and I printed it out on the printer in the department, I went to pick it up and I found out that somebody else had completed his homework for him. So for example, the task was to do a storyboard of any book. So somebody, I don't know who, picked it up and did a storyboard of The Introduction to QFT by Michael Peskin. Of course, we couldn't turn that in, nor could we turn in this one, a book report on Introduction to Quantum Field Theory by Michael Peskin. But anyway, it's a friendly place, right? People like to contribute. Okay, but my talk today is about deep learning, right? Deep learning and particle physics. And these days, deep learning is everywhere. Machine learning is everywhere. If you take a drive through San Francisco, you see deep learning on billboards and machine learning this, machine learning that. I think all you need to get $1 million investment in your startup company is say the words machine learning, and somebody will give you $1 million, right? So what is machine learning anyway, right? Everybody has a different view of what machine learning is. Mostly, we just use tools from the consumer industry and apply them to problems that we have, right? We don't need to invent these things ourselves. And in the end, mostly deep learning is just another way to do statistics, right? We do statistics to understand our data. So what is statistics? Well, statistics is that this awesome overlap between engineering and math and hacking and computer science, right? We do it because we need to understand our data. And the reason is that our data is not that pretty always. Right? If you're doing an experiment where you're looking for example, unicorns, maybe unicorns are difficult to find, but once you find the unicorn, you're pretty sure you have a unicorn, right? It's like pretty unambiguous. There's the horn, there's the unicorn, you're done, right? The problem is in particle physics, we're looking for new particles. It's very rare that you have such an experimental result where you say, here's my data, boom, one collision, one example, I can conclude that there's a new particle. And there's a caveat. There's a couple of examples in history where this has been done. But typically, it's more complicated. Why is it more complicated? Because the scale of the experiment we're dealing with is enormous. So for example, the Large Hadron Collider, one of the initial goals of that machine was to discover the Higgs boson. So how do you do that? Well, for example, you can collide protons together, and the gluons inside those protons can slam together, fuse together to make a Higgs boson, which can then decay to two B quarks. The problem is the Higgs boson, you never see it directly. It lives for 10 to the negative 23 seconds, right? You never actually see the Higgs boson. So you can't say, look, we made a Higgs boson, and therefore we discovered it the way you could with a unicorn, right? The reason you can't do that, even though it decays into these two Bs, is that there are lots of other ways you could also make the same signature in your detector. It's not a background-free analysis. There's lots of other things that happen in the standard model. For example, if two gluons fuse together, they could just make another gluon, which gives you two Bs. Or if you're looking for two quarks to fuse together to give you two Bs, there's lots and lots of other ways. And these will drown out the occasional example of a Higgs boson. So the reason that we need to use machine learning and deep learning specifically in particle physics is because our data is not unambiguous, right? Here's an example event from the Large Hadron Collider. So what you're looking at is a picture of what happened inside the detector. The beam goes into the page and also out of the page, so it happens here on this surface. And this is a slice of a cylindrical detector. So you're seeing stuff spray out sideways. And this we interpret later as an electron, and here we say this was probably a top quark, but it's not trivial, and you could misunderstand what's what and say, oh, this was actually a photon, etc. Here's another example. This is a three-dimensional view of an event where you had probably a Z decaying to two taus, and then one of those taus decayed into a muon and the other one decayed hadronically and gave you some spray in your calorimeter. But it doesn't say, I'm a tau on it, right? It says, oh, here's some evidence which you can statistically infer to be more likely to be a tau than anything else. Okay. But we have big problems to solve, right? We can't say, well, look, the data are difficult to understand, so whatever, the problem is too hard. The stakes are enormous. These days, we know very well that we know very little about what the universe is made out of. Most of the matter in the universe is not the kind of matter that we have around us. It's dark matter. Most of the energy in the universe is not even in the form of normal matter or dark matter, right? It's dark energy. So we're at this really excellent moment in physics, an era I like to call precision ignorance, where we know very well that we know very little about the universe, right? And that's an opportunity, right? Don't be discouraged by that. That says, wow, maybe in 100 years, people will look back on this era and say, I wish I was a grad student back in 2017 when nobody had yet figured out whatever it is we're hopefully going to figure out and revolutionize physics with, right? It's better than having everything figured out. But at the same time that we know very little, we have these awesome tools, right? The Large Hadron Collider, we have space telescopes. So we better do our best to use the data from these machines and extract all the juice that we can from these things, okay? Because the questions are not just what is dark matter, right? The questions are very broad. There's a lot of open questions in physics. How many spatial dimensions are there? What is mass anyway? What is the pattern of the particle masses? And as Flip mentioned, I recently wrote this popular science book, which is sort of an introduction to all the open questions in physics. Instead of writing a book about all the things we do know, I thought it'd be more fun to talk about what we don't know, to inspire a new generation of people to explore the universe and try to answer some of these big, fat questions. If you're interested in the book, I'll be at the Cellar Door bookstore later today with my co-author, Jorge Cham, who's the guy who does all these awesome graphics. So anytime you see something which looks like a really cool doodle, it wasn't me, okay? It was Jorge. Jorge's an awesome guy to work with. He and I wrote this book together. It's full, it's like 400 cartoons in it. There's some silly humor. There's a fart joke or two. Anyway, it's about the big questions of the universe. Okay, but let's narrow down and not think about the big questions of the universe. Let's think about one specific question. What are we doing at the Large Hadron Collider? What would we love to do? Well, we'd love to discover a new particle, especially a particle that nobody anticipated. So how do you do that? Well, statistically, often what you're doing when you're looking for a new particle is you're comparing two different hypotheses. One is the standard model, so you got your set of existing particles. And the other one is the standard model plus one new particle. Maybe this is a SUSY particle, maybe it's a graviton, whatever. You have two hypotheses, right? And in statistics, it's most powerful when you're comparing two hypotheses, and then you're asking the data, you're asking nature, which of these two theories do you prefer, right? So that's the game. If it's a very simple hypothesis, and you have a very simple experiment, then you can imagine thinking about how to use the data to answer that question. So say, for example, this is the standard model, and this is the standard model plus some particle. And this axis here is some experimental observable that you've cooked up. And that's the job of the experimentalist. Conduct a system which can determine which of these two hypotheses is the one that nature prefers by giving different outcomes. So maybe it's the number of a certain kind of event you see in your detector, where this, of course, is the frequency of occurrence. If you're lucky, and you can discriminate between two hypotheses using just one thing that you observe, then it's pretty straightforward what to do. You say, well, there's a distribution of outcomes for my new particle hypothesis and a distribution for my no new particle hypothesis. I'll draw a line here. And if I see more events than above, if I'm on this side of the line, I'll say, yay, I discovered a new particle. If I'm below the line, I'll say, sorry, I didn't discover anything today. That's pretty straightforward in a one-dimensional problem, right? We're never in a one-dimensional problem. We always measure more than one thing. And then it gets tricky. Okay? Say you have 2 dimensions. 2 things you're measuring about your data. And now you have a distribution of possible outcomes under the 2 hypotheses. So here's one of them, and here's the other hypothesis. What can you do? Well, you could just draw 2 straight lines. You can say, well, I'm going to declare discovery and buy my ticket to Stockholm if my result is in this box. You could also say, well, this looks pretty good too. I could just draw a single line here and say all of this stuff. Or I could say, why am I drawing straight lines, right? It's a complicated problem. I'll draw a curve. But there's an infinite number of possibilities there. How can you solve this problem? Well, nearly 100 years ago, smart guys Neyman-Pearson figured this out. They said, actually, we know exactly how to draw the optimal boundary, the one that will give you the best performance, the smallest possibility of missing a discovery, as long as you're willing to assume a certain fixed false discovery rate. They said, if you want the best, the most optimal decision boundary, the one that you don't miss a Nobel Prize, then you just need to take the ratio of these two likelihoods. The probability of seeing your data under one hypothesis divided by the probability of seeing your data given the other hypothesis. Pretty simple. A likelihood ratio. You say, what's the chance of seeing my data under these two different hypotheses? If it's greater than some ratio, then I'm declaring discovery. So these guys figured it out, right? And this is really cool because it allows you to map. So this is that likelihood ratio. And here, for example, is a signal-like region and a background-like region. And as you move from 0 here to 1, for example, here, it maps out where in your potentially high-dimensional space of experimental observables you should declare discovery and where you should declare non-discovery. So it solves this problem for you, right? It says, I know exactly which regions of your experimental space are discovery regions and which ones are not. And remember, there's no, I didn't tell you anything about the dimensionality here. This could be one-dimensional, it could be 1,000-dimensional, right? This is a very general, very powerful statement. Awesome, right? So seems like we're done. We know how to do this. These guys figured this out 70 years ago. But that's only true if you know how to calculate this thing, the probability of seeing your data under a hypothesis. Can we do that? Well, in particle physics, can we generally calculate the probability of seeing some data given an arbitrary theory? Well, let's take a look. Often, the discovery is pretty simple, right? Say, for example, we're looking for a new particle like the Higgs boson, and it's a case in a resonance, and all the events tend to pile up in one spot in some single experimental observable, maybe the mass of the two B quarks, for example. If you can conduct an experiment like this, where you have a single dimension and your two hypotheses have a very stark difference, then you're in luck, right? Then you can say, well, I'm going to ask nature, which of these two hypotheses do you prefer? And nature usually says this one, right? And you can calculate this ratio. You can say, well, I have my model for what my data should look like as a function of whatever it is I'm calculating it. And I can tell you the data prefer this one, right? This a better chance of having seen this data under the no new particle hypothesis. But that's rarely the case, okay? And in general, we work in a higher dimensional space, so we need to use the likelihood ratio, which only works if we can calculate this, the probability of seeing some data given theory. You might think, well, we have a lot of smart theorists. Surely they can tell us what we expect to see in our detector under some new theory. If Flip comes up with a theory of a flipperon or something, certainly he could tell us, here's what a flipperon would look like in your detector, right? Well, what are the steps involved there? There's a lot of complicated pieces, okay? This part here, where the new particle is created, that's pretty well under control, right? But after that, the particles shower, and then they hadronize, and they interact with the detector. There's a lot of pieces here which are actually quite difficult. So let's think about what this function would look like if we had it, okay? I'm going to break it into all those pieces. So it's the probability of seeing the data given that you have some final state particles, right? So this is just creating those particles in the first moments of the collision, times the probability of creating those final state particles given some showered particles, so after showering, and then sorry, I went backwards. Starting from some theory, the probability of getting some hard scatter products, given those, the probability of some showered particles, given those, the probability of some hadronic particles, given those, the probability of actually seeing something in your detector, right? And all of these things here, this one and this one and this one, you don't observe. So to calculate this, you have to sum over all possible intermediate states that can contribute, right? All these things that are unobserved, you have to integrate over them. All right, well, we have a lot of computers. We can do integrals, right? But in order to do that, we need to understand detector response, hadronization, and showering, and all of these pieces, okay? This part here, the probability of seeing something produced given the theory immediately after the interaction, this is pretty well defined. And actually, the theorists have done an incredible job of building tools that can calculate this for you given almost any theory. So that part is pretty well under control. All right? The rest of it, however, is kind of a nightmare. Given that you produce certain particles, we don't have a good understanding for which particles will shower and how they will shower. Given that you produce the showered particles, we don't really have a good understanding of how hadronization happens. Given hadronic particles, we don't really have a good analytic way to describe what you will see in your data. What we do have is a solid understanding of the microphysics. Like, I can tell you what happens when a muon slams into a slab of copper. Okay? You know, it radiates and the photon pair produces and all the ionization happens. But I can't write down a function that says, here's the probability distribution for energy, you know, in all of your calorimeter given any arbitrary muon. And the reason is our detectors are really complicated. Here's what it's like flying through the liquid argon calorimeter at Atlas. Well, it goes from one particle to 3 particles, right? It knocks off other particles. Those particles pair produce. You get a shower of particles. Pretty soon, you have a huge number of particles. Now, this is a simulation that tells you we can understand it, right? I can tell you what will happen. I can give you an example. Say one electron comes through, I can give you an example of what might happen, but I can't, again, write down the analytic function that tells you the distribution of outcomes all over your detector. And that's what we need. If we're going to calculate the Neyman-Pearson the likelihood ratio and use Neyman-Pearson, then we need to know the probability distribution of our data given an arbitrary theory. But it's very complicated. So while we have a solid understanding of the microphysics, what we need is an analytic description of this high-level physics, right? But I don't even know how to write that down because the dimensionality of the problem is variable. It depends on how many particles are produced in the intermediate state. I don't even know how to write down something which would ever satisfy that. So that doesn't mean we're stuck, right? We've solved these problems. The way we've approached it is instead of trying to figure out what this PDF looks like and writing down a function, we built an iterative approach. We said, we know how to do this part, creating some final state particles given your theory. I'm just going to generate a bunch of examples. And from that, I'm going to say what a shower might look like. And from that, I'm going to say what hadronization might look like. And from that, I'm going to say what a detector response might look like. So I get a bunch of examples. Okay? So what I can do is make an arbitrarily large sample of events drawn from this function, even though I don't know that function myself. Okay, so I don't know, I need this function, I want this function. If I had this function, I could do excellent statistics, but I don't actually know this function because this space is very high dimensional and I don't have an analytical description. But I have a tool which will allow me to generate examples from this function, as many as I need. All right, so then we can just reverse engineer the function, right? If you have a bunch of examples from a function, somebody has some function hidden in their pocket and you don't know what it is, but they'll give you examples from it, right? Then you can figure out what it was. You can say, well, here's a bunch of examples. All I need to do is a histogram. Histograms are easy. Every first-year particle physics grad student can make a histogram, right? It just counts the frequency of the times you saw different examples, and then your histogram is essentially an estimate of the original function, right? That works pretty well. And you can even be more clever about it. So in the case of a single resonance, you know, even if you can't calculate this spectrum exactly, if you can simulate a bunch of examples, you can build up a PDF that allows you to calculate these likelihood ratios. You can say, oh, well, in the case of a new particle, I expect to see a bump here, so I can calculate the ratio of these likelihoods because I just have all these examples. I can reconstruct the PDF. Okay, well, I said I could make an arbitrarily large number of these, right? Well, how many do you need? If you wanted to describe a one-dimensional distribution, how many would you need? Well, let's just say, for example, 100. So you got a nice, smooth description of what this thing looks like. Maybe you need 100 examples. Okay, that's one dimension. How many do you need for an n-dimensional distribution? Because remember, the data that coming out of Atlas is about 100 million dimensionality. Well, it's not n times 100, it's 100 to the n, because you need to describe each of these dimensions and the correlations between all of these dimensions. So as soon as n gets large, 2, 3, 4, 10, 50, then 100 to the 50 is a very, very big number, right? There's 10 to the 80-something particles in the universe, right? So very quickly, the number of examples you need to describe a high-dimensional space is larger than the number of particles in the universe. And we certainly don't, even Google doesn't have enough processing power to describe that. Okay, so if this data is a 100 million dimensional vector and we don't have the PDF, then even this iterative approach where we build up the PDF doesn't work. Okay? So now we're sort of stuck. What do we do? Well, this is where machine learning comes in. And this is the point of my talk, is that machine learning is helpful for dimensional reduction. It solves this problem. It says, I'm going to take your big, fat dimensional problem, I'm going to make it simpler for you. Okay? If, for example, your hypothesis, your discovery region is buried in some 2 or higher dimensional space, right? Then what you need to do is use neural networks or some other equivalent tool to find this information and boil it down into a one-dimensional distribution, right? To map it for you. If you can map all that high-dimensional information into one-dimensional output, into a one-dimensional new variable, this classifier output, then you can solve the problem. We can simulate enough events to describe the distributions in one dimension. We can't do it in 100 million dimensions or even in 50, but we can do it in one. So if we had a tool which could do that for us, then we could calculate this likelihood ratio. We could deal in one dimension, right? So if we're speaking to our AI servants, here's our task for them, right? Find me a function. This is the space of my data, which goes from some high dimensionality, r to the n, down to one dimension. But I want it to contain all of the same hypothesis testing power as this likelihood ratio, right? If we knew this likelihood ratio, we would just use that, right? But we don't know it. So basically, we want you to find some function which does that same thing from n dimensions down to one dimension. That is the task we set for machine learning. Okay? If you can do that, then boom, we can discover new particles. Okay? So what do? How do we solve this problem, right? Say you are the AI servant and somebody's giving you this task. How do you go about solving this problem? Well, you might say, I don't know in general what this function should look like, but I'm going to try something. I'm going to say maybe this function here can be built out of a pile of little functions, right? I don't know what your function is going to look like, but I'm going to say I have a pile of little functions, and I'm going to try to put them together and approximate your function. So without justification, I'm going to say maybe this function looks like this. Okay? It has some parameters, w0 and wi, which are on the inputs, and it's a function of a sum of the inputs. I'm just going to weight the inputs in some amount and then pass them through some nonlinear function. Okay? So I'm going to use this as like my building block, and I'm going to put a bunch of these together and try to figure out how to put these together to approximate the function you want. Okay? And here's an example of this function, this h of x, right? And I have not explained why this works, right? I've just said, let's just try this approach. Your activation function can look like this, for example. If it's negative, it's 0, and if it's positive, it's 1. And you can have sharp ones or smooth ones or whatever. Okay? And here's a graphical way to think about this function. Okay? This is your input data, n-dimensional input, 100 million dimensional atlas data, or 50,000 dimensional data from cat videos on the internet, whatever. Okay? This is your input data, and this is the thing you want. You want this output. It has to be one-dimensional. So in the way I described it, remember, it just takes a weighted sum over the inputs. Okay? So I'm just multiplying the inputs by a number and adding them up, and then passing them into some function. So each one, this is the input, and the line represents a weight. And then I add them all together, and this has some activation function inside of it, which evaluates, and then it spits out. And this, of course, is modeled after biological neural networks. This is the way they work. They're connected to each other. They send each other messages, and those messages are weighted depending on the strength of those neuronal connections. But just a graphical way to think about the function. Okay? Now we have the question, well, what weights do you use, right? If you've constructed this arbitrary function, it's just going to be a mess unless you know what the weights are. How do you figure out what the weights are? We just kicked the problem down the road. We said, we want that function. I said, well, maybe we can build that function with these little blobs, and now we have to actually figure out how to put those blobs together to make the solution. Well, every set of weight values defines a different function. Right? If I choose a set of my weights, then I get a certain output. If I choose a different set, I get a different function. Right? So now we have this functional space. What we can do is we can define whether or not our function is working well. So we define the error. So for every w, that's a weight value, that defines my function, that tells me what y is. Right? So y is a function on my inputs, and it depends on these weights. I'm just going to define the error. I'm going to say, well, how close is y to the truth? You may say, the truth? You already have the truth? You had the truth in your pocket the whole time? What are you doing? Right? Why are you wasting our time? Well, remember, we have an infinite number of examples. We just don't know what the function is. So I can generate examples for you for the Higgs boson or for the fliperon or whatever, but that doesn't mean that I know what this function should look like, right? I do have the truth. I know for each example whether it's Higgs boson or not Higgs boson, right? So this is called supervised learning. It says, well, how close is your approximation to the true answer? Just because I have examples, remember, doesn't mean I know what the function is. We're trying to build a function which mimics the truth. So I just define this. I say, well, the distance from the truth, call that thing quantity squared. This is going to tell me whether or not my function is any good. So now I have a huge space of functions, and I know where in that functional, I know how to evaluate whether one of the functions is good. Okay? So we have a weight space, which determines our functions. We have a quality metric, which tells us whether or not our function is any good or not. All we need to do is search the space to find the one that has the best quality, right? Seems pretty simple. Just search the space. But this is a generally unsolved problem, okay? Maximize a function over an arbitrary space. If you know the solution for how to solve that general problem, then write it down right now and put it on the archive, because you could solve problems in about 50 different fields. Okay? It's in general an unsolved problem if you don't know something about the function, because the function could have a spike here or a spike there. If you don't know anything about the function, then basically the only solution is to scan brute force every point in that function to find the maximum. We don't have time for that. So instead, we'll start in an arbitrary point in this space. We'll evaluate the error, and then we'll look for the gradient. We'll say, well, in which direction does the error get better? And then we'll just do a gradient descent, and we'll search for a minimum or a maximum equivalently. Okay? And this is the learning part. We say we start with an arbitrary function, which is going to be terrible, because we just randomly chose it. And because we know whether it's good or not, we can see in the neighborhood which direction to get better, and that's the learning. Okay? And so this is called backpropagation. You take the performance of the network and you say, it didn't work well. How would I have to change the weights to make it better? And you push that backwards through the network and figure out how to iteratively improve the weights. And it works. And you can make you can find networks which mimic the solution that you need and work pretty well. And you can have even more complicated networks. You can say, well, I don't just need to have a simple connection between my inputs and my output. I can have intermediate layers. These guys take the outputs from these nodes and recombine it with another nonlinear function to give me more complicated output. So I can build an arbitrarily complex function. Just think of a neural network as a very, very flexible, arbitrary parametric function with a huge number of parameters. And then you've just turned it into the problem of how to find the right set of parameters so the function does what you want. Okay? So how complex can it get? Well, for a long time, people were using machine learning and particle physics, and it worked pretty well. This is in the 90s. People thought, oh, wow, this is pretty cool. Let's use it. It works pretty well. And there was this theorem that was floating around that said that all you needed was a single hidden layer. And with a single hidden layer, if it's large enough, you can approximate any function. People thought, well, that's pretty awesome because multiple hidden layers are hard to do. So I'm glad that one hidden layer will work. And people sort of hit a wall. They said, neural networks work pretty well, but they don't work that well. Okay? The problem is that it's true that you can approximate any function with one hidden layer. The problem is that you might need a huge hidden layer. You might need like 5 million nodes or something crazy. Okay? The problem is that networks with more than one layer are very difficult to train, because remember, how do you train this thing? You start from a random place in functional space and you look around to see how to improve it. You're pushing that information into this node, and then you're pushing that information into this node. By the time you get back here, you have 3 gradients. So these gradients get very, very small. It's very hard to figure out it's very hard to train these effectively. As a result, people just use networks with one node. And what that means is that these networks are not good at learning nonlinear functions, because you get a little bit of nonlinearity in every node. Remember, the activation function is nonlinear. But if you want to learn a really complicated function, it's not necessarily the case that with a small number of nodes in a hidden layer, you can model a really complicated function. And in particle physics, we use nonlinear functions. For example, what's the best way to discover a new particle? It's calculate its invariant mass. Invariant mass is a very nonlinear function on the Cartesian momentum, right? So what people figured out about 10 years ago was you can't just treat a neural network as an artificial grad student and say, here's a bunch of data, figure it out for me, right? That's what we wanted. We said, well, look, we took the data. Is there something new in it, right? It just didn't work. And here's an example. Here's an analysis I worked on Atlas. You couldn't just throw the data at it. If you gave it too many inputs, it got confused. And so what we had to do was pick and choose different inputs and see which one would optimize the performance. So this is a search for Higgs decaying to 2 taus. Here's a list of variables. And in different channels, they chose, the dot tells you that they used that variable. And so for example, in this mode, to choose which variables to use, they had to try every single combination of variables. Okay, so there's like, 20 here. They tried the network with all 20 variables. It didn't work well. They tried all 20 networks with 19 variables. They tried, I'm running out of numbers here. They tried a huge number of networks, all with smaller and smaller sets of variables, so they found the one that worked well. And look at these variables. Like this one is 2 of the other variables multiplied by each other, right? Or here's 2 variables, the ratio of 2 variables, right? Certainly a neural network should be able to figure that out. If there's like a key insight in the ratio of 2 inputs, is the neural network so dumb that it can't figure out how to divide 2 things? Yes, because we have a simple neural network, okay? It can't build up complex functions if you only have one hidden layer. It just can't do it. So then about 10 years ago, there was a revolution in computing, and people had good ideas for how to train networks that had multiple hidden layers, right? These things are harder to train. They take more CPU, they take more examples, they take clever techniques for how to build the structure, but they're capable of doing nonlinear functions much better. So I thought, well, let's try them out on some classic problems, okay? Well, what's a classic neural network problem? Well, here's one that Facebook spent like hundreds of millions of dollars on. It's, is this a picture of Sylvester Stallone, right? So you have an example picture of somebody's face, and then you have a picture of them at a party where they're turned slightly, and Facebook wants to tag it for you, says, oh, is this your friend Sylvester Stallone? So it figures out like what is his face, it takes that picture, it rotates it, like this is an algorithm called deep face. It's amazing how much energy and resources in our society are spent on these kind of trivial problems. But because Facebook spent time on this, they developed a lot of cool code, and so did Google and other people like that, and we can use that code, right? Just the same way that we use silicon technology that the consumer industry invented for particle physics, we can surf on the backs of frivolous consumer desires in order to solve important problems. So I wrote a paper now a couple of years ago saying, let's see how this works for particle physics. So we made an example problem. Here's a problem where you have a heavy Higgs boson decays to another Higgs boson, decays to a Higgs boson, and you get this final state, 2 W's and 2 B's. And then, of course, you can't have anything be unambiguous, so there's other ways to make the same final state. For example, 2 top quarks give you 2 W's and 2 B's, right? The question was, can the deep network automatically discover how to discriminate between these two, right? So we said, well, let's just give it dumb information. Let's just take the data. This is all simulation, of course, but let's take simulated data, just like the PT of the things that we measure, or the XYZ momentum, okay? The jet B tags, the missing energy. And if you look at any one of these variables, black is background and red is signal, you see there's not a whole lot of discrimination, right? No one-dimensional projection of any of this information contains much at all. But we're clever, right? We know how to solve this problem already. We say, well, if I was given this job, I would say, well, let's look at the mass of these 2 B quarks, because in the case of a signal, it should look like a Higgs. In the case of the background, it should not, because it doesn't come from a Higgs. And then let's also look at all these other places, like the WBB mass added together should look like the mass of this guy, but that's not the case here. Whereas if I add the W and the B together, I should get the top quark mass. So we came up with 7 clever variables that we would have used if we did the analysis, okay? And in these variables, there is some good discrimination. You see, like, look, oh, there's some peaks here. And again, in the one-dimensional projections, they're not awesome, but clearly we've done something right. Our brains worked. Our 20 years of particle physics knowledge helped us. So we said, well, let's give it a try. So what we did is we took some neural networks, and the way to read this plot is, this is signal efficiency, and this is background rejection. So what you want is to be here. You want to be able to find a region that keeps all of your new physics and rejects all of the background, right? That would be background rejection of 1, signal efficiency of 1. So the way you judge one of these curves is how close is it to up here. Okay, so the first thing we did was we said, let's take a neural network and give it all the low-level information, just like the raw detector outputs, right? The Cartesian momenta. And this is how well it does, the black line. Well, that's pretty good. Well, what if we give it our clever variables, okay? The ones that we thought of. Well, look, it did better, right? So this is the problem. The problem is the neural network didn't figure this stuff out itself, right? Here we're just using a standard shallow neural network, a one hidden layer neural network, okay? It couldn't figure this stuff out. It said, it tried, it did its best, but our intuition improved it. And this is the statement of the problem, is that there's a gap here. Clearly it's missing something, because when we give it a clue, it does better. And that was the problem. We thought, well, if it's missing something, how much else is it missing, right? And if you combine the low-level information with our clues, it does even better. Okay, so this is essentially just to set up the problem. Find an example of a case where a neural network fails. Okay, and we tried other approaches also. Well, what happens when you use a deep network? Well, here's what happens. If you give it only the low-level information, right, no clues as to about how the masses should be calculated, you get this kind of performance, the black line, which is pretty good. If you give it only our clever variables, right, the things we thought of, it does worse. Okay, so if you say, forget about all that information, just focus on these issues, right, it doesn't do as well. And if you take the low-level information and you add in our clues, it doesn't improve at all. Okay? So our clues clearly don't contain all of the information necessary to solve the problem, and the deep network doesn't need any advice, right? It isn't helped out at all by getting our clues. Okay? And here's a direct comparison. If you take the best performance from the shallow network, where you have both the low-level information and the human assistance, you get this curve. And this is the deep network with no clues at all. We just gave it the raw data and said, go. Okay, so the deep network does better than even the human-assisted neural network. All right? So does that mean that the age of singularities are here? Well, I, for one, welcome our new AI overlords. But I would say that we have identified example cases where traditional neural networks fail to discover all the discrimination power, right? So that's the problem we were seeking to tackle. And cases where adding human insight helps a traditional neural network. And what we saw is that deep networks succeed without any human insight, right? And in fact, they outperform human-boosted traditional networks. So that was exciting. Yes, question?
What was the revolution? What does deep networks, I had my idea over this subject, so what does deep networks do, or what is the multiple thing, what do they solve exactly?
All right, so why does it work better? Okay, well, I might have a slide on that. Let me see. No. The reason is that the deep network, what can it do? It can build nonlinear functions. Okay, the traditional neural network just can't. It's basically just building simple linear functions. And those just don't work as well because the solution requires nonlinear combinations of the Cartesian momentum.
I thought you said long back that you're building gradients, and gradients get smaller and smaller.
Yes, okay.
More and more. So what revolution happened there? Not in this stuff.
Right. So why is it now possible, whereas before it wasn't? Great question. I've asked my computer science colleagues that question as well. And the answer is computing is cheaper. And so you can just push on those gradients longer, right? That's the number one answer is we just train for a lot longer. And even though those gradients are small, they're there. And just keep pushing and keep pushing and keep pushing. And eventually, enough GPUs later, you get better performance. So these solutions were impractical 10 years earlier because the computing wasn't there. Okay? That's the number one answer. Number two answer is there is some human cleverness also. The way you construct the networks, the training strategies, the details, how often you update the weights. There are some clever ideas there for how to make these networks trainable, whereas before they weren't. But I think the number one answer is we just train longer. Yeah. So it's just that we used to think this is impossible, and so we stopped considering it. And then when computers caught up, we're like, oh, look, now it's possible, so let's try it out. It's just that simple. Okay. So this opens up a new window to us, right? Now we can say, well, now we can analyze higher dimensional data. This shows us that we've been overlooking some power of our data because we thought the high dimensional problem was too hard, right? We weren't giving our networks the full high dimensional data because we thought it was too hard. We boiled it down for them. But those heuristics where we boil things down threw away information. We lost power to discover new particles by doing the dimensional reduction ourselves. So let's go back and think about how much dimensional reduction is happening and think about what might be possible. So at the very, very lowest level, right, the data that just comes out of the detector is like, 1 times 10 to the 7. It's very, very high dimensional. That just counts the number of detector elements in a typical LHC detector, right? It's huge. But that's not really the problem we need to solve. If you only look at the detector elements that actually fired, then maybe you have thousands of detector elements. And then if you do reconstruction, where you say, I'm not so interested in the individual ionization trails that an electron leaves, I'm really interested in just the track of the electron. You perform reconstruction, you get down to maybe a 100-dimensional problem. And then if you're only interested in some fraction of the detector, you're looking for muons or something, then you can select it to get a subset down. In the end, we want a one-dimensional problem because this is really the only dimensionality that we can handle. Maybe 2, sometimes 3. But in the end, we have to boil down our data to 1 dimension so we can fill those histograms and calculate the likelihood ratios. So what's possible? Well, I'm suggesting that this step here, right, can now be handled by neural networks, right? Instead of doing a heuristic where we go from a selection to analysis by calculating some complicated variable that we think might be good, we can now ask our neural networks to do this part for us. Great. Does that mean they can go deeper? Can they start here? Could they start here? Could they even start here? Could we just strap the neural network directly to the fire hose and say, call me when there's something new? Or maybe a better approach is this one. We want to retain some intuition for what's going on. Nobody's going to read a paper that's written by a neural network that says, look, trust me, the flipperon is real, right? Nobody's ever going to believe that. We want to see what's going on, right? So maybe a better approach is this one, is to retain these human signposts in thinking and say, well, instead of doing this part myself, I'll let the neural network do this, and I'll let the neural network do this, and I'll let the neural network do this, and I'll let the neural network do this. And I think this is a more reasonable approach. So we followed that up and we said, well, let's try to do some other problems with deep networks. So for example, we looked at jet substructure and we looked at jet flavor classification. I'll tell you briefly about those. One problem in understanding jets at the LHC is that when particles decay, sometimes because of the huge energy of the LHC, they're going so fast that the particles decay and particles land up on top of each other. And so when you're looking in your detector and you're saying, well, was this 1 particle or 2 particles, that can be an important way to discriminate your signal from your background. And so if you look at, for example, 10,000 examples where you have 2 particles and 10,000 examples where you have 1 particle, you see clearly on average there are differences. But in individual cases, it can be pretty hard to tell. Is this 2 particles? Is this 1 particle? It's a pretty difficult problem. But it's an excellent problem for machine learning. It's excellent, especially because computer scientists are really, really good at vision analysis. They spend a lot of time writing neural networks that can look at an image and analyze that kind of data. Mostly because they're starved for real problems. Like there are people who spend their whole PhD thesis writing neural networks that can answer the question, is there a cat in this internet video? Seriously, why? Not because they care about cats, right? They're like, oh, here's a hard problem, and I have a bunch of data that's available, and so great, I don't care. And that's one lesson is like, if we can talk to the computer scientists, convince them that our problems, which I think are a little bit more meaningful than the cat question, are suitable tasks, then they can actually help us solve real problems rather than spinning their wheels on the cat video problem. Anyway, so we said, well, how well can we do here? Let's try to use a deep network to identify the difference between these two. So here we have another one of these curves. It looks a little different because I'm using a log scale, but it's the same basic idea. You want to be up here. And there's a few variables created by very clever theorists to try to figure out whether this is one-dimensional or one particle or 2 particles. And if you just use one of those variables, jet mass, you do okay. If you add another one of those variables, you do better. If you take a BDT and combine these high-level variables in essentially a shallow network, you do much better. So that's this blue line. The red line is what happens if you say, we're not going to use any ideas from the theorists, we're just going to give it the images and say, go. okay, just like we did in the previous case. What you get is a little bit of improvement, not a whole lot. I mean, you get some improvement, but it's nothing to really write home about. The lesson here is theorists have done a really, really good job of figuring out what the critical variables are. So remember those steps I talked about where a human applies some heuristic to boil down a high-dimensional problem to a lower-dimensional problem. Sometimes that's not that great, and you leave a lot of information on the floor. Sometimes they've done a really good job, and they've approximated really what's going on, the truth. So there's not a whole lot of information lost. This is still very valuable, though, because then we know. Before that, we didn't know. Well, is this doing a good job? Is there some awesome variable these guys are missing? Well, this tells us there's not a whole lot of extra information that's lost.
Is the red line the best we could ever do, or is the best we can do given the training?
Excellent question. I definitely cannot say it's the best we could ever do, right? In 15 years, somebody could say, you know, they thought deep networks were great, but that's just because they never tried a 100-layer network because that was impractical then, and now we have quantum computing, so it's trivial. We don't know. I can't tell you what the maximum performance is. We can say this is pretty good. Yeah, I think the theorists deserve a lot of credit here. But yeah, we don't know that there's not something missing. Absolutely.
So how about the quality of the data? So you're saying you could come up with a different network with 100 layers, but could you change that agreement between the red and the blue by changing the quality of their data?
What do you mean by the quality of the data?
Maybe your data has too many errors. You're sampling the training set that you're using is non-ideal. It has a lot of errors. Can you make it better by increasing the quality of that? More sampling or lower errors?
You could improve it certainly by having more examples. There are no errors here per se. I mean, every example is correctly labeled, yeah, because it's all simulation. One issue though is how well does this example describe reality? What these networks are learning is the difference between simulated this and simulated that. This is only relevant if we're simulating something which is realistic. At some point, we might be learning things which are just features of our simulation and not actually useful in the real data. It's an important issue.
There's one question. So it's like in this deep network, how many layers are you doing it? Is there just like a good number to go with?
Yeah, so how do we construct these deep networks? We found in this example that after about 7 layers, you don't get much improvement. So we tried 7, 8, 9, 10 layers, but we don't get much improvement after about 7 layers. If you look at the paper, you see some studies of how deep it is and how complex it is. We also tried things like, let's just use 1 layer, but make it really, really big. and we showed that you can get better performance as that layer gets big, but the layer has to be really, really huge to mimic this performance. So that's another lesson, is that deep but thin networks do a lot better than shallow but fat networks because the deepness gives you the nonlinearity. And so you're better off, if you have a certain minimum number of nodes, or maximum number of nodes, you're better off making it deep than wide. We applied it to another problem. This is the problem of understanding whether a jet has a B quark in it. And here, this is a very complicated problem, and people developed lots of heuristics. So we tried various approaches. Again, this is signal efficiency versus background rejection. The traditional approach, this expert approach, is this black line. And this boils down a lot of information from tracks and vertices, all combined together in complicated neural networks, et cetera, boiling it down. It does pretty well. What we found is if you just throw the tracks at the neural network, just the raw tracks to say go, it does better, but not always, right? Some cases it does worse. But if you give it a little bit of help, you say, well, what about tracks plus I'll do some vertexing for you, finding the places where the tracks overlap. Then it does better, okay? And if you do the tracks and the vertices plus the expert advice, then it does even better. So what this suggests is our neural networks here are not ideal. There's room for the network to improve. This information is structured in such a way that all of the information, the expert information, is a subset of the information of this, which is a subset of this information. So this pink line, in theory, should get the maximal performance because it has all of the information. It just has not been able to achieve it. So we tried up to 12 layers here, but we're not able to improve the performance. So what this tells you is the expert variables have removed some information. So there is information that's missing. However, throwing just the lowest level information in the deep network doesn't work in this case. So this requires a more complicated solution. It requires a more complicated solution. One tricky bit about this approach is that the number of tracks in an event is variable. Sometimes they'll have 7, sometimes they'll have 42. And the networks I showed you have a fixed number of inputs. So we had to try lots of interesting structures with like recursive networks, where you don't necessarily have a fixed structure, but you have a recipe for how to build a neural network for an arbitrary number of inputs. So these can accept a different number of inputs based on the event. But this shows you there's still work to be done in improving these techniques. All right, so deep learning is a very powerful tool. It offers essentially faster ways to learn nonlinear functions. And since we don't know what the PDF of our data is, and we have a bunch of examples, we need to do something like this. We have a lot of tasks in high-energy physics where we have traditional heuristics where somebody said, well, this is a hard problem, so I'm just going to reduce the dimensionality using some reasonable arguments. Those are reasonable arguments, but they've lost some power. There's something you're missing in that simplification. However, it doesn't mean that humans are outmoded yet, right? If you give it garbage or you don't train it well or your simulation doesn't reflect the actual data, you're not going to learn anything useful. All right, thanks a lot for your attention.
Any more questions for you? Are we completely uninterested in how does the neural network do it? Because, can we extract any physics about how exactly different layers do? Because eventually we end up in like artificial intelligence giving us a piece of paper. We have to figure out, like, is it right or not?
Yeah, absolutely. We're very interested in how it does it, right? Ideally, we would apply neural network to a problem. It would find some awesome solution. And then we would figure out how to map that solution into some quantities that were relevant to the human brain with a physics intuition so we could learn something. That's difficult. We're working on solutions to how to do that now, but that's difficult in general because these are very complicated beasts and prying them apart and figuring out why'd you do this and why'd you do that is hard. One thing we've done is push information backwards and say, how do you approach this how do you classify this event, how do you classify that event, and then trying to examine the decision surface and saying, in some space that we think is important, what decision did you make? And so for the example, the first example I gave you, we did that, and we figured out why the deep network was able to do better than the shallow network. And the answer is that the deep network rediscovered the invariant masses, so we could see that it was choosing events near the peaks of the invariant masses, but it had feathered out the side away from the peaks. So the traditional neural network just rejected all the events that were too far away from the peaks, but the deep network found a way to keep those by adjusting it and feathering its decision boundary a little bit. So we were able to learn something, but we don't have a general strategy yet for how to reverse engineer what the neural network has done. And I agree that's an issue because we'd like to learn what is done. How do we know? Right? We can ask, if you come up with a new variable, I can tell you whether it's using that information, but figuring that out the other direction is hard, right? You can't ask it, and in order to answer whether it's using that information, you need to already construct the variable. One thing we've done is try to create spaces of generic variables that span the space of all possible variables, and then try to map the neural network into that space so that we can interpret it, but it's difficult. Yeah. It's a hard problem.
First of all, it seems like, how do you know there's a unique weight? I mean, is this a statement that you had to go down this error path to find some meaning of your training set? Presumably there's still some error left over even when you get to meaning.
Yeah. You never get perfect classification.
So you already know that the answer that you're getting at the end may still not be the best.
You're not guaranteed a global minimum, no. Because in general, that's an unsolved problem.
So the only justification is at the end, it looks like it's getting something right.
Yes. What you can do is, it's stochastic, right? There's a lot of randomness in these search strategies. So what you can do is run 4 of them and see if they all converge to the same answer. If one of them goes wildly into the weeds and finds something really awesome, then that's great. That's one thing you can do, but you're never guaranteed that you found a global minimum, no.
And it never runs into cycles and all that kind
Oh, they get stuck. Yes, sometimes they get stuck in local minima. But there are strategies in the training to try to help avoid that. But yeah, they can get stuck in a local minimum, absolutely. Yeah, min-we is trying to solve that problem, right? Yeah, it's a big min-we problem, yes.
Yeah, I mean, in many body physics, we have strong correlation of the relative ground states are in application. Is this a tool to apply to those types of problems?
Yeah, if, for example, you have functions which are slow to calculate and you want to evaluate them more rapidly, then certainly. I mean, I know people at Irvine, like Steve White, is using machine learning for density functional theory, for example. Absolutely. It's a way to like rapidly calculate in a higher dimensional space. You learn a bunch of examples, and then use the machine learning essentially as a complicated multi-dimensional interpolation. Hello?
You mentioned one limitation is the accuracy of your simulation.
Yes.
High-definition model is
Absolutely. Absolutely.
How do you convince yourself, or but you've shown that these new techniques do better, but I don't know. I mean, how do you quantify that uncertainty in the simulation?
Yeah, great question. So you need to know that what you're doing is reasonable, right? So you can use a strategy that we use for other quantities, right? You take, for example, think of your network as a function, okay? And the question you want to know is the information it's using well modeled or not? Okay, so what you do is you take some other data that's not the data you're going to use to answer your actual physics question, but maybe it's adjacent to it, it's the control region. Push that through your network, and then you compare the simulation to the network output. If it's wildly off, then you know the network is using some correlation which exists only in the simulation. If not, then while the simulation may be imperfect, your network is using only information which appears to be well modeled. But then, of course, you have the problem you have to extrapolate that confidence from your control region to your signal region, but that's a core problem in high energy physics anyway, right? We always have this issue of identifying control regions where we validate our model and then extrapolating into the signal region. We have less intuition here, but we still can validate the model in adjacent regions. It's an important problem. Another approach is to develop networks which are insensitive to these differences. So for example, we recently put out a paper about this using adversarial networks to try to constrain the optimization. So for example, you might say, give me a network which performs well, but I want you to perform well to give similar performance under two different options. So for example, you say, here's my Pythia sample, here's my Herwig sample. I want you to not be sensitive to these differences. So you can constrain the optimization using another network which checks up on those. So we have a paper out last year on that. You can try to just build networks which are insensitive to these systematic uncertainties. So that helps you. But then you have to identify those in advance, right? Yeah. So.
Any other questions for Daniel? All right, so for anybody who is curious about science or knows people who are curious about science, the book signing is at 5:45 in Canyon Press. For the undergraduates, signed copies of Daniel's books will be the prize for our first annual physics hackathon. And for everybody else, I'd like to thank Daniel for his time.
Thank you very much.